Hello, this is Mrs. Decker, and this is Objective 1F, drawing potential energy diagrams for exothermic or endothermic processes and being able to label the following four things: activation energy, delta H, products, and reactants. Before we get started with today's lesson, we want to do a little bit of a warm-up on Objective 1D, endothermic and exothermic changes, and what clues help you figure them out. So go ahead, take a look at these examples, and when you're ready, we'll go over the answers. All right, boiling water is an endothermic process. The clue that helps you know that is boiling, and you need to put energy into the water to get it to boil. Freezing water is an exothermic process because you need to remove energy from the water in order to get it to freeze, and the clue that helps you is freezing. Fireworks are also an exothermic process, and the light, fire, sound are all clues that help you realize that fireworks are exothermic. This is what an energy diagram for a chemical reaction looks like. So the general shape of the graph will be similar whether it's an endothermic or an exothermic reaction, but there are a few slight differences between endothermic and exothermic reactions. So you will need to be able to recognize that and figure out what, based off the graph, whether the reaction is endothermic or exothermic. So we're going to look at the different parts of the graph first, and then we'll try to figure out whether it's endothermic or exothermic. So you need to be able to label four things on the graph. Two of them are the reactants and the products. So this flat spot here is the reactants, because the reactants have some energy already stored in the bonds of the molecules. So they're starting off with a certain amount of energy already in the molecules. And then this here is the products, because there is a certain amount of energy left in the products after the new molecules have formed and bonded. So you should be able to label reactants and products. Whether a reaction is endothermic or exothermic, it always takes an input of energy to get the reaction started. It just is about how much energy needs to be put in versus how much energy is given off the reaction. So the energy needed to start a reaction is called activation energy, and we abbreviate that capital E, A. So the amount of energy it takes to get from what's in the reactants up to the top of the curve here, that is the activation energy. The fourth thing that you need to be able to label is delta H, which is the change in energy between the reactions. Okay, and delta H is the energy from the products to the reactants. That's the change. Okay, so to calculate delta H, you would do the energy of the products minus the energy of the reactants. So now that you know how to label these four things on the graph, you need to know how to read the graph and find out what the change in energy and what the activation energy is. So if we're looking at the graph, the energy of the reactants is 80 kilojoules. The energy of the products is 160 kilojoules. The energy it takes for the reaction to start is the activation energy. So to calculate the activation energy, we are going to take the value from the top of the curve here, which is 240 kilojoules, and subtract the energy that is already in the reactants. So when you do that, you get an activation energy of 160 kilojoules. To calculate delta H, it is the energy in the products minus the energy in the reactants. So it's always products minus reactants. So for this reaction, it is 160 minus 80. So the delta H is positive 80 kilojoules. So now the last step is to be able to recognize whether this is an endothermic or an exothermic reaction. So if you remember, an endothermic reaction, energy is absorbed by the reaction. In an exothermic reaction, energy is released. So if you look here, the reactants have less energy than the products. That means that this reaction is endothermic. So when you're looking at these diagrams and the amount of energy in the products is higher than in the reactants, that tells you that this is an endothermic reaction because energy has been absorbed by the reaction. So here's another example of an endothermic reaction. The potential energy of the reactants is less than the potential energy of the products. So that tells us that this is an endothermic reaction. So here is our activation energy from the reactants up to the top of the curve. And then here is our delta H from the energy in the products to the energy in the reactants. This transition state here at the top of the curve is when the molecules are in a transition state between the reactants and the products. So the molecules are different from both the reactants and the products, and because they are transitioning to their new products. Here, this activation energy, ReV, that stands for reverse reaction. So when we're looking at chemical reactions, most of them are reversible. They happen in both the forward and the reverse reaction. So the delta H is going to have the same value, whether you're looking at the forward or the reverse reaction. It's just going to have the opposite sign. The activation energy, however, is going to be different for the reverse reaction, so you'll have to calculate that. So if we're looking at a forward reaction, we're looking at the reaction going this way from reactants to products. If we're looking at the reverse reaction, we're looking at the reaction going this way from products to form reactants again. All right, so here is another energy diagram that we will need to label. So again, remember this first flat part of the graph is where the energy of the reactants is, and the second flat part is where the energy of the products is. If we're looking at this graph, the reactants have more energy than the products do in this graph. So this represents an exothermic reaction because energy has been released into the surroundings during the reaction. The activation energy is from the energy in the reactants to the top of the curve. And to calculate activation energy for this, it would be 100 minus 40. So our activation energy for this reaction is 60 kilojoules. And our delta H, remember, is the energy from the products to the reactants. So to calculate delta H, we have to start with the energy in the products, which is 20, minus the energy in the reactants, which is 40. So our delta H for this reaction is negative 20 kilojoules. And so here is just another labeled exothermic energy diagram. We have our reactants here, products here, activation energy from the energy in the reactants to the top of the curve, and then delta H from the products to the reactants. So you have some practice graphs in your packet to work on. Go ahead and do that and let me know if you need help.